In this video, we will practice integrating using inverse trig rules. And here are the three inverse trig rules that you need to memorize. Before we get started though, first you need to understand how you know that we're going to use any of these rules in the first place. We have solved problems that were very similar to this using natural log. In fact, if there were an x up here instead of just a 1, we would be doing use substitution and using a natural log rule right now. And here's how you know. It's all about the degree of the numerator versus the degree of the denominator. Right now, the degree of the numerator is 0. There are no variables up here. The degree of the denominator, ignoring the radical, is 2. That's the highest exponent. If the degree of the denominator is 1 more than the numerator, then you can probably just do use substitution and use a natural log rule. But notice that the degree of the denominator is 2 more than the numerator. That is your clue that this will be one of these inverse trig rules. Now, which one are we going to use for problem number 2? I see that we have the constant minus the variable squared. And I see in the arcsine rule, we have the constant minus the variable squared. So I'm betting that this is the rule to use. To make it look even more like this rule, I'm going to rewrite this part with parentheses so that we have something squared, some quantity squared. Having 4 and then x squared is the same as having 2x in parentheses squared. You square the 2 and square the x, you get 4x squared. But in this form, it's easy to see that u is really 2x. So that is the substitution that we're going to do. Let's let u equal 2x. That means that u prime will equal 2. Now we are ready to do the substitution. So far, I have this. Instead of writing dx, I will write du divided by u prime, which is 2. On the next step, this 2 is going to end up in front of the integral sign. We now have a perfect match for the rule. Notice that a is 1. A is always the square root of the number that you see right here. So maybe I'll add that to my little list. I'd like this to be green. So a is 1. Remember that. So let's go ahead and use the rule to integrate. So I will have arcsine u over a. So I shall write arcsine u. Normally I would write u over a, but I just said a is 1. So there you go. Plus c, and don't forget the 1/2 that we have in the front. Now let's substitute 2x back in for u, and I have 1/2 arcsine of 2x plus c. So this is the answer to problem number 2. Which rule do you think we will use for problem number 6? Probably the arctangent rule. This is the only rule that does not have a square root, and we see no square root here. Also, this is the only rule that has a plus sign, and you see the plus sign right there. This is already in the form that we need. So we see a squared, so 4 must be a squared. So that means that a is the square root of 4. So a is 2. We see x minus 3 squared, so that must be u. So u is x minus 3. U prime is 1, so nothing will really change because of that. Let's go ahead and do the substitution. So we have the integral of 1 over 4 plus u squared. Instead of dx, we can just write du. Normally I would say du over u prime, but it's a 1. Now we can apply the rule. So it's 1 over a, so that's going to be 1 over 2, and then arctangent, and then we have u over a. I think I'm going to go ahead and put the x minus 3 back in right now, so that's going to be x minus 3 over 2 plus c. So that's it for number 6. Okay, which rule do you think we will use for number 10? It's either going to be the arcsine or the arcsecant rule, because I see the square root. So for the arcsine, we have the constant minus the variable. For arcsecant, we have the variable minus the constant. I see the constant minus the variable here. So I'm thinking it's going to be the arcsine rule. Based on the arcsine rule, the a value is going to be 1 because the square root of 1 is 1. So a is 1. I'm thinking let's let u equal the natural log of x because that is what is being squared and we need u squared. In that case, u prime is going to be 1 over x because that's the derivative of natural log. So let's go ahead and make our substitution. So we're going to have x and then the square root of 1 minus u squared. All right, we have that 1 in the numerator. Instead of dx, we will write du over u prime, which is 1 over x. Notice that we have this x, which will multiply by 1 over x to make 1. In other words, these cancel each other out. So on the next step, we will just have the integral of 1 over the square root of 1 minus u squared du. This is a perfect match for the rule. So we can integrate by writing arcsine, and then we need u over a. But a is just 1, so it's just arcsine u plus c. Let's go ahead and put natural log x back in for u. So we have arcsine natural log x plus c. Easy peasy, y'all. Which rule do you think we will use for number 14? I'm thinking we will be doing the arctangent rule this time. I see no square root, and there's a plus sign, and that's what we have going on here for arctangent. Based on the rule, a is going to be the square root of 7, because a squared is right here. So just take the square root of the constant. That's your a value. How about u? Well, we need u squared, and we see cosine squared. So u must be cosine. That means that u prime must be negative sine x. Let's go ahead and do the substitution. So for now, we still have sine x in the numerator. And we have 7 plus u squared. This line does not need to be that long. Instead of dx, I will write du over u prime, which is negative sine x. Notice that we have a sine x in the numerator and the denominator, so these are gone. We still have a surviving negative sign. Let's put that in the front of the integral on the next step. So now I have 1 over 7 plus u squared du. Notice how this perfectly matches the rule. Time to integrate. The rule says 1 over a, so we will do 1 over radical 7. arctangent u over a becomes arctangent u over radical 7 plus c. Don't forget the negative sign hanging out in the front. That is still there. Putting cosine x back in for u, you arrive at the final answer. Okay, which rule do you think we're going to... Wait a minute. I started to say which rule are we going to use, but the degrees, man. The degree of the numerator is 2, and the degree of the denominator, at least inside the radical, is also 2. So that makes me think that maybe this is not going to be an inverse trig problem. This problem turns out to be pretty tricky. We will wind up using inverse trig functions for part of it, but then not using inverse trig for the other part. What do I mean? Well, I'm going to end up using my a plus b over c rule. That's where I split this up into a over c plus b over c. Now, what in the world could I be talking about? Where's the a, b, and c? Let's color code this. So I have my a and my b and my c. So this is going to be the a, this is going to be the b, and all of this, the entire thing, is going to be the c. So I can split this up as a over c plus b over c. And really, I want to write these as two separate integrals. So far we have this. On the next step, I'm going to simplify the x and the x squared. One of these x's will cancel out. Also, I'm going to take this 3 and move it outside of the radical. I'm going to move it outside of the integral and put it in the front. So now we have this. One of these integrals looks like we will need an inverse trig function, but one of them doesn't. Notice that the first integral, the difference in degrees is only 1. The degree of the numerator is 1, and the degree of the denominator is 2. When the degree of the denominator is 1 more than the numerator, we should be able to simply do u substitution. So let me come back to that. For the second integral, the degree of the numerator is 0, then the degree of the denominator is 2. Because the degree is 2 more than the numerator, this looks like an inverse trig function. Which of these trig rules do you think we will use for the second integral? Well, let's see. I do see the square root, so arctangent is out. I see the variable squared minus the constant. Let's see. Variable squared minus the constant, that's arcsecant. So this is the one we will probably need. Setting up the u substitution for the first integral, let's let u equal everything under the radical. So u will equal x squared minus 4. That means that u prime will equal 2x. The second integral matches the trig rule perfectly. We just need to acknowledge that a is going to equal 2. It's the square root of this constant. So let's go ahead and do the substitution. So we will have the integral of x over the square root of u. Instead of dx, we will write du divided by u prime, which is 2x. I'm just going to leave this the way it is for now. Notice that we have an x in the numerator and another one in the denominator. These will cancel each other out. On the next step, the 2 in the denominator will become a 1/2 in the front. And I'm going to rewrite this slightly. The square root of u in the denominator would be the same thing as u to the negative 1/2 power. Now we are ready to integrate. So using the power rule of integration, me bring down my u. I'm going to add 1 to this exponent. That's going to make this a 1/2 power. Then I divide by my new exponent. But dividing by 1/2 is the same as multiplying by 2. So I have this. But don't forget about the 1/2 that's already in the front. And yeah, these are going to cancel each other out on the next step. So moving on to the second integral, I'm going to bring down the plus 3. Now it's time to use the rule. So I have 1 over a. Remember that a is 2. So I'm going to say times 1 over 2. And then we have arcsecant, absolute value. It says u over a, but we didn't do any u substitution. So I'm just going to put x over a, x over 2, plus the constant of integration. Substituting x squared minus 4 back in for u, we have x squared minus 4 to the 1/2 power. And I could write this as the square root if I wanted to. And the 1/2 and the 2 cancel each other out, so those are gone. Plus 3 times 1/2 is 3/2. Arcsecant, absolute value of x over 2 plus c. That was kind of a lot, but this is the final answer.